Okay, we know that sine squared t plus cosine squared t equals 1. And we're going to use that to eliminate t. Right? We don't want to solve one of these for t and plug it back into this, because then it'll involve inverse trig functions and it'll be ugly. So we use the Pythagorean identity in cases like this. So what is sine t? Y minus 6 divided by 5, right? And x is, or cosine t is, you're going to subtract 1, divide by 5. So x minus 1 over 5. So the equation of a circle, so it's an ellipse if these are different, right? So if these values are different, then one axis is stretched more than the other. But if they're the same, then essentially what we have is y minus 6 squared plus x minus 1 squared equals 5 squared. And so we have a circle, because on the x and y axis, this tells you how far you go out from the center. And since it's the same, then it's a circle. So if we were to sketch that, you should be able to sketch that. Center is 1, 6, and radius of, so it's not going to quite make it down to the x-axis. It's getting worse. Okay, let's try this. There we go. Okay. All right, so something like that. Center is, h is 1. K is 6. Radius is 5. Okay, initial point. So then they're saying that we want to do this from pi over 2 to 3 pi over 2. So that's possible. It doesn't give the whole circle. In fact, that probably just gives, pi over 2? That probably just gives half of the circle. So we can find out which part of the circle we get by the terminal point will be, or the initial point will be the xy ordered pair when the t is the starting value of pi over 2. So when t is pi over 2, we're going to get x equals and y equals. So cosine is 1, so we're going to get 6, right? Pi over 2. Cosine is 0, we're going to get 1. Pi over 2. Sine is, that's 1. 5, so we're going to get 11. You get the point 111. So the initial point is right there, 111. And then the terminal point will be the ordered pair xy when the t is that last value. So when t is 3 pi over 2, that will also be 0. And so you're going to get x equals 1, and then that will be negative 1, so you're going to get 1, 1. So now the question is, there's two ways to get there, right? So it's either going around like this, or it's going around like this. So how can we find that out? Well, if we just get a point in between, right? So pick a t value in between. So the obvious choice here to make life easy is, yeah, so halfway between pi over 2 and 3 pi over 2 is pi. So when t equals pi, we get, that's going to be negative 1, so we're going to get x equals negative 4. And sine is 0, so we're going to get 6, negative 4, 6. So we're over here. Okay, so, and you may have already kind of suspected that because of the way the unit circle works, right? So we know on the circle, 0 is at like 3 o'clock, and then as you rotate counterclockwise, pi over 2 is at the top. But we saw that there's lots of ways, there's more than one way to do this. So if this was sine and this was cosine, then all those bets are off, right? So everything's different then. So watch out for assuming, because this point was the starting point and this point was the finishing point, oh, it's going to be on this side. So don't necessarily assume that. Verify it, okay? Verify that it is indeed this, left side of the circle. So therefore, which way is the curve traced? Well, so the curve is traced in the direction for increasing t. Are you guys bored? All right, so this is for increasing t this way. You get this point first, then this point, then this point, and so that's going to suggest which? Clockwise or counterclockwise? That's counterclockwise. So you just have to get enough points close enough together so that you see as t increases, how's the curve like swept out? And so in this case, initial point, halfway point, terminal point clearly means it's being swept. The points are emerging this way. They're coming out this way. So that's counterclockwise.
Thank you.
Yeah, sure. Other questions about this or other examples? Okay, so we're going to do more of this parametric stuff. Okay, so here's a parametric function. X equals t cubed minus 3t squared. And y equals negative 2, quantity 2t to the fourth minus 3t squared plus t minus 4. Okay, and we get this interesting looking curve here. So suppose we wanted to talk about, as we come, so let me get this. So here's for increasing t on that graph right there. This is showing the direction of the curve. So I'm showing t values from negative something to positive something, right? So the value of t is down there in that slider, and then it's showing all the corresponding points for all these values of t. Okay, so suppose we want to know. So look at this again. So what is happening? So when you look at this point now, yeah. So what through here? So what could you say about something mathematically up and around here? So based on what you're seeing, what could we talk about?
There's a lot of points in the area.
Okay. A lot of points, okay.
And because t is going up by a steady.
Right, so exactly. T is increasing steadily. So for some increase of t down here around -2, what do we see for change in x and change in y compared to for the same change in t around here? What do we see for the change in x and the change in y? Right, and so what's that about? So mathematically, how do we show that mathematically? Rate of change, right? And that's rate of change is found by derivatives, right? So we could look at dx dt. We could look at dx dt and let's find dx dt. What is dx dt? That should be easy by now. 3t squared minus 6t. Okay, and then dy dt. So we're just going to apply the negative as we do it. So it'd be negative 8t cubed plus 6t minus 1. Okay, so let's look at that point. Let's find those values at t equals negative 2. Or let's do negative, should we do negative 1? No, negative 2. Let's do negative 2. Get it in there. Down there. So negative 2. So I want you to find the point on the graph and the derivatives at t equals 2. So what's the point on the graph? So at t equals 2. What's the corresponding point? And what are the derivatives? And then check your work with the person next to you. And then same with at t equals 1. Make the math easy. Okay, so what'd you get for the coordinates at t equals 2? Nice enough. 3, negative 18? 3, negative 3, negative 18. Okay, what'd you get for dx dt? 0? Okay. Negative? Positive 53. Oh, my bad. I meant negative 2. Negative 2 and negative 1. These numbers weren't making sense. Sorry. T equals negative 2. Do what I mean, not what I say. I was showing you down here, right? Where it was negative 2. So the point is negative 19, negative 16. Derivatives, first derivatives. $51. Okay, can we interpret those numbers? So this should be easy. So what's the meaning of this ordered pair, negative 19, negative 16? That should be easy. That's the point we got on the graph for when the parameter is negative 2. So now, what about 24, 51? So dx dt is 24, dy dt is 51. What do these numbers mean? So for every change of t of how much? So no, it was good. It's just for what? Yeah. So it's for a change of t of 1, dx if it kept that rate, would change by 24. And what does that mean that the x would change by 24? What does that mean? Yeah, so it's positive 24, so we expect the point to be 24 units to the right of where it is now. Okay? But we know that when t changes 1, this rate changes a great deal, right? So really, we want to just think about what's happening very close to t equals -2. And what this means is for a small change of t close to -2, the change in x is 24 times the change in t. So you can write it this way. dx is... And so it really makes more sense to talk about just a small change in t close to -2, like from -2 to -1.99. Okay? That makes more sense to talk about it that way. A really small change in t. Then your change in x would be 24 times whatever you chose for your change in t, near t equals -2. So x is changing at a fast rate compared to t. So y even more, right? So for a small change in y, change in t, you expect the point to go up 50 times whatever little change in t you pick, close to -2. Okay, what about for t equals -1? Where are we at now? -3, 6. So that's up, yeah, I've got that pretty close to here. Okay, and what's dx dt? 9. dy dt? 1? Is there, the people get that too? Confirmed, okay. So what's happening here? dx dt before it was 24, and now dx dt equals 9. Slowing down. Which direction slowing down?
Still positive, slow.
Yeah, so
To the right.
just the right. So just the right, if you think about just the x-coordinate of the point, so we're moving right. Still moving right, because it's positive, but a lot less for the same change in t, right? Like a third as much. It moves right a third as much for the same change in t. And what about y? So that's way slowed down, right? And so that's what you were seeing when that now for the same change in t is increasing at a steady rate. So for the same change in t, you're getting much less of a changes in y and x around this bend here. But then when it gets away from the bend, so what do you expect like right now for dy dt, right now? Really high negative value, right? For change in t, it had a lot of change, negative change in y. Okay, so the meanings of these numbers are important, and they're kind of like speed, but they're really with respect to t. So you think of as t changes, t is not necessarily time, but as t changes, how did the x and y coordinates of your points change? Okay, so are there any points here of interest? So if we're looking at this curve, I was thinking something more basic than that. Yeah, how about a maximum, right? So we say can we figure out what the coordinates of the very highest point up here are? Because there is some high point, you can clearly see. So what's the math behind a high point? So all the stuff that we're talking about. What's true at the maximum? He's saying dy is equal to 0. So for a change in t, we want y not to change. Would that be like the high point? Yeah, so we can take, if we want the max, we can take dy dt and do what? So equal to 0. Okay, and what is our dy dt? Minus 8t cubed plus 6t minus 1. Okay, and so that is a cubic that can't be factored. So we would need another way to solve this, right? So we could solve this graphically. I can open up a new thing here, and I could do y equals negative 8t cubed plus 6t minus 1. No, I want x. So what am I looking for here? I'm looking for where that's 0, right? I want that thing to be 0. So looks like there's 3 zeros here. Which is the one that we want? Where's the maximum? Close to. Yeah. Why is it not working here? Did we make a mistake? No. Minus.
Yeah. Are we supposed to be looking at where t is on the maximum on the graph?
Right. So this is the x value.
No, those are t values. Those are t values. That's a y t value.
What's going on?
Positive one.
Oh, right. Okay, t values. So our t value is close to what? Right, very good. Okay, so the t value is close to, up here at the top, there we go. Right, negative 1. Okay, so the value of t at that maximum point is close to negative 1. So we go back to our graph there, and we get it exactly as almost negative 1. Negative 0.94, basically. So I'm looking for the 0 of this. So what gives me 0? And that corresponds now to these are t values, right? So I want that dy dt to be 0. And so that's going to be around negative 0.96. And indeed it is negative 0.94. Yeah?
If we don't have that slider, how do we justify which one is the closest one?
So this would be something you'd be doing with your graphing calculator. But I just erased everything. Okay, sorry. Let's see here. So what do we have for dy dt? Minus 1. And we found that this is going to have 3 zeros. One of those zeros is at t equals negative 0.94. And that's this one that gives us that maximum. And so then how would we find the highest y value? What would we do? What's that? Compare all the 0 values? No, we know we've got it. It's just how do we find that y value that's the highest? Yeah, so we're gonna take that t and plug it in, and that gives us that point. Gives whatever that high point is. Okay, so because this is kind of not a great decimal, it's the idea of it. So make sure you just understand the idea that the maximum is going to be where your dy dt equals 0, because for a change in t, y doesn't change at a high point. Okay? And then another one of those zeros would be, another one of those high points where dy dt is 0 is going to be somewhere around here. So where t is about 0.8, around t equals 0.8, you're going to get another place where dy dt equals 0, and that's indicating a high point. And then what was the third one then? There was a third dy dt equals 0. Right, which is indicating a minimum, right? So your high and low points locally are going to be where for a change in t, y doesn't change, so dy dt equals 0. And so when I showed you that graph before, we saw 3 zeros of that graph. Those were the t values for these this high point, and this low point. Okay, so find where the graph has a vertical tangent. This you can do algebraically. You won't get a cubic, okay? So find where the graph has a vertical tangent. Find the ordered pairs. Go. Premise here, to get a vertical tangent, what did you do? For a change in t, we want no change in x. That's what a vertical tangent means. For a change in t, no change in x. So that means dx dt is 0. And what was our dx dt equation again? Okay, this one's very reasonable and manageable. How do we solve that? Factor out 3t, and we get? All right, so we like this a whole lot better than that last one. T equals 0 and 2. So t equals 0. We want to know what point we get. What point do we get? 1, 4. Does it make sense with the graph? 1, 4. Right there. And so let's zoom in on that. So if I zoom in right there, here at the nose, there it is, 1, 4. And that's where, for just a moment there, change in t means no change in x, so that the point is moving vertically, if you want to think of it that way. But so for small change in t, no change in x, vertical tangent. Okay, and what was the other one you got? So when t equals 2, you get? Negative 3? Negative 15? 18. Okay. So we might not have been expecting that one. We might have thought, oh, this thing just keeps like going to the left, but it actually, if we scroll down here to negative 18, oh, here I am at t equals 2. Look at that. Okay, so if I zoom in, what do I do? I want to zoom in. No, not that way, the other way. Whoa. Yeah, so here's that point, negative 3, 18 right there. And actually, so what we saw before that was heading to the left actually curls back around and heads vertical for this moment at t equals 2, the point negative 3, 18. And so as you go down further now, it heads back to the right and actually crosses the x-axis again. Question?
Are you recording?
Yeah. Uh-oh, what's happening here? I'm going the wrong way. Back to my original graph here. Oh, gee whiz. There we go. There we go. Okay. Okay, so the idea, so this like vertical, so the dy dt equals 0 gives you horizontal tangents or potential high points and low points in the local area, right? We had three of those, one here, and one here, and then where dx dt is 0 is going to give you like left and right maxes, like the maximum value of x, right? Or vertical tangent would be like the max x, and then over here the locally the max minimum x in this local area down here was at -3, -18. Okay, so what about, so if I just picked a t value, say at t equals -0.5, we've got a graph of y and x. We could talk about what is dy dx, which is the derivative that you're used to. So even though this is defined parametrically, x and y are defined in terms of t, we still have a graph in the xy plane. And so it still makes sense to talk about at any point on this graph, what is the rate of change of y with respect to a change in x? And so how could we do that? Any ideas? How could we find dy dx? It's, oh, we don't want to, so no, we don't want to get, so trying to get y as a function of x? No, so very unhappy, right? No, can't do that. All right.
Plug in t for each dy or each one with respect to time, and for one of them,
Yeah, which would you divide? Which is on top?
dy.
Yeah, so if you take dy dt and divide by dx dt, that will give you dy dx. Okay, so our dy dt was -8t cubed minus 6t plus 6t minus 1 over 3t squared minus 6t. And so now at t equals -0.5, what does that equal? I'm going to make a formula here. So negative, let's call it g of I think I've probably already done this. So I'm going to make a function out of this. But notice what's different about this dy dx than what you're used to. So we have dy dx, but there's something different about it. What's different? What's that? Yeah. It's in t, right? So it's still, even though it's the change in y with respect to x, it's not a function of x like you're used to, right? It's still a function of t. Okay? So did you get -0.8? So at t equals -1/2, it's -0.8. So what does it mean? So for a change in x close to where t is -1/2, y changes by -0.8 times as much as whatever change in x you picked. Okay, so what does that mean? Where will the next point be relative to the point? Lower. Yeah. So if you change in x would be an increase in x to the right. It's going to be down almost as much as you went to the right. Right. 80% of what you went to the right is going to be down from there. So let's see if that's accurate. So we're going to set t equal to -0.5. It's about as close as I can get. Right there. So does that confirm the number that we got? So for a change, we're saying for any, here we are at t equals negative a half. For some change in x, how much does y change? Well, it's going to be negative, it's going to be down, it's going to be like what, 80% of negative 0.8 times as much as that change in x that you picked. Okay, so suppose we wanted to find the equation of the tangent line. So what's the equation of the tangent line at this point? What do we need to find the equation of a line? Yeah, so the y-intercept isn't very convenient. So because we don't know where that's going to intercept the y-axis. So, but what else could we have to get that point and slope, right? And then we can, so the point slope form is m times, we ever do that form? So that's actually a better form of a line than y equals mx plus b. So then, but this is not the y-intercept, right? This is any point on the line. So that's a point on the line AB. Okay? So do it. Find the equation of the tangent line at t equals negative 1/2. You've got everything you need to do that. All right, let's get some of you involved here. Let's see here. How about Jet? How about the point? How did you get this point that we're going to have?
You took the point to where t equals negative 1/2.
Okay.
So then I ended up having 0.121.
Yeah.
And then was my a value, and then my b value was 5.127.
So we got some ugly. Anyone have an infraction form? 1/8. 1/8 and 41/8. So that'll be exact. So someone else get that? Good. All right. Cool. All right, and then take it from there. Let's see. Heidi. So what else do we need then to write this equation? Okay, which is? That's our negative 0.8. So we got our negative 0.8. X minus an eighth. And we can leave it just like that. We don't have to make it in mx plus b form. This is just as valid, just to leave it just like that. So if I do that, if I graph that line, y equals negative 0.8 times x minus 1/8 plus 41/8. What should we see? Well, at this close-up view, what should we see? So I'm way zoomed in on this. So what should we see zoomed in on that point? I'm about to graph the line. What's that? Hits the other, just once? Just touching it? I'm way zoomed in. Yeah, it's like you're not gonna be able to see the difference almost, because we're so zoomed in. If I zoom out, then you can see that it's tangent at a point. But if I zoom in enough, the function is essentially, oh, what happened?
I think it's 33
33/8? I think so too. Wait a sec. Didn't graph it. I guess it's yeah. Curve is outside the region shown. What's going on? No, it's not 33/8. I don't think. Definitely not. I think what was happening there, so I think I would agree with 41/8, and I think what was happening is, as we were getting really close, it had to do with, yeah, maybe. Let's just try one more time. Come on. There we go. No. Okay. Don't move. Here we go. Very curious. Yeah. 77/16. Curve is outside the region shown.
I got 5.
Really?
That's like 1/8 away.
Nope. Curve is outside the region shown. 41/8 seems to be winning. I think that's because of.
Did you try 39? No, that would.
No. Let's do. What are we trying to do? We're trying to put -1/2 into this, right? And B is -1/2. 5.125. That's 41/8. Congratulations. No, it's 5. That's 41/8. So it's the way that this thing graphs parametric equations. It kind of connects the dots. So it's connecting two dots, and instead of curving out, it's cutting the corner. So that the tangent line is right, but the graph of we've zoomed in so far that it's actually a different line connecting two dots. That's not the actual curve of the parametric equation. I hope that makes sense. So this view, not to worry about it. It's tangent at that point, right? Okay. All right, so what about the second derivative? So what about the second derivative of y with respect to x? Let's take a look at that. Okay, so how are we going to do that? So we've got the dy. What we want then for the second derivative is it's the derivative of the first derivative with respect to x. Okay? So, but this, remember, this is in terms of t. Okay? So this is in terms of t. So what we're going to do is we're going to take that derivative with respect to t because that's what we can do. All right? That's dy dx. And then divide that by dx with respect to dt. Okay. Why? Because our dy, again, our dy dx is in terms of t, so we're going to take its derivative with respect to t divided by dx with respect to t, and that'll be our second derivative, dy dx with respect to x. Okay, so how are we going to find what is dy dx? What was it again? It's up here. I wrote it down. That's right there. Right? But I've got a's instead of x's. So we need to take, or a's instead of t's, right? So these are all t's. So we need to take the derivative of this with respect to t. What's it going to be? Well, these are t's. These should. So I was just doing it in terms of a instead of t, but yours should be t, right? Your dy dx should be like this with t's, right? So how do we take the derivative of this with respect to t? Quotient rule. Remember quotient rule. So here we go. Do it fast. Low d high. Check my work. I'm going to go fast. Low d high minus high d low. Please check. I'm going to go fast. All over. Low squared. How did I do? Okay, that's just this top part. And that whole thing over. Oh, come on. It's just a few symbols. Babies. All right. dx dt is what?
3t squared.
So this is the derivative of your first derivative with respect to t, or dy dx dt, and then dx dt. So then what do we get? So we can actually combine these, and we get just put this over this thing cubed. See that? So we put this whole numerator over this thing cubed. So I'm not going to write it again. I'm just going to erase and rewrite this as a cube. I'll leave that for a moment, though.
What are you doing for me? I'm sorry?
So when you take this divided by this, it's just going to be times the reciprocal of this, right? So we're just going to get 3 of those in the denominator. So I'm not going to rewrite it. I'm just going to erase and change the 2 to a 3. Can I do that now? So that's what we got. Okay, and so then if we were to put a number into this, it would say t equals 0. Let's make it as easy as we can. T equals 1. So let's put t equals 1 into that. And what are we going to get? We'll get -3 times Negative 18 minus negative 8 and 5. Is that negative 3? Check my work. Times 0. We like that. All over. 3. So negative 3 cubes and negative 27. Check my work. Did I do that right? And so what do we get? Negative what? So this is negative 9 times 2. Is it just negative 2?
Yep. Yeah.
I love it. Okay. So what is this? This is the rate at which the rate of change is changing with respect to x. Okay? So that's the second derivative. Or for a change in x, how much does the rate of change change? Okay? So for a small change in x, your rate of change is going to change by negative 2 times whatever your change in x is. So that would be the way to summarize that. If you were around t equals 1 and you let x change a little bit, your rate of change would change by negative 2 times as much as your change in x. That would also indicate concavity of the graph, right? So this is second derivative is negative, which means it's concave down, concave down. The rate is decreasing. Rate of change decreasing. At t equals 1. Whatever point on the graph corresponds to t equals 1. Okay? Any questions on that before we get to areas? We're going to do areas next. Okay, so here we go. Areas. So areas of parametric function graphs. So let's talk about, so back when y was a function of x, in the good old days, how did we calculate area? We used what? No areas of curves that are weird shapes, right? We need integral, right? We did that back at the beginning of the semester. And we said start from x1 and go to x2. And what did we integrate? If y was equal to the function of x, it would be whatever that f of x was, right? Dx. And this was like the area of a really thin strip, right? Rectangular strip. And the dx is not just with respect to x. It's part of the math, right? The height of the strip was the function value. The width of the strip was dx. And so that's the area of a rectangle, height times width. Dx is part of the mathematics. It's part of the math, right? Area of the strip is height times width. Okay, and then we added all those up starting at x1, ending at x2. Okay, so fx is the same as y, right? It's just y. So if we're going to do this in parametric, we're going to follow the same pattern. We're going to sum up a bunch of lots of little thin rectangular strips. And so essentially area is y dx. So what is y? We know that y is some function in parametric, some function of t. So let's call x is, say, p of t, and y is q of t, okay? That's parametric functions. X and y are each some function of a parameter t. So then y is our q of t. And if x is p of t, then what is dx? If x is p of t, then what is dx? P prime, so it's the derivative, right? P prime of t dt. So d of x is the derivative of t, and then like kind of like a mini chain rule there, times dt. But now we're in terms of t, so it's going to be from t1 to t2. And so then this is our area formula for parametric functions, because it's going to be in terms of, it's going to be with respect to t. But it's still, what? Height times a little chunk of width, right? Still a rectangle. Height times width. Okay, so let's talk about if we were to start at t equals -1. Where's that? Somewhere around there. And let's go ahead and get the so yeah, so fine. So at when t is -1, what's our point? Can we find it? T is -1. We already did that, right, earlier? What is it? -3, 6? Okay, so I want to look at starting there and then ending at this x-intercept down here. This x-intercept is essentially t equals 1.451. And that ordered pair is -2.26, 0. So what would happen if what would it represent if we took the integral from, I'm running out of room, so I got to erase. So get this all on your paper, and I'm going to erase and start again.
Wait, why are you saying that t equals 1.4?
Because that's the x-intercept.
Oh, okay.
That's where it crosses the x-axis. Can I erase? I'm going to erase and start over because I need room. Am I good? So what would it mean to find the integral from -1 to 1.45 of q of t p prime of t dt? So I guess what I'm saying is, what area will this find? Okay, what area will this find? So is it -3, 6? Get off the screen. There we go. Did I say 1.451? Yeah, okay. I want to be as close as we can. Okay. So in order to kind of think about this more, let's break this up. So isn't this the same as the same integral from -1 to 0? And was 0 at this vertical tangent here? Wasn't that point t equals 0 right here? Of q p prime dt plus the integral from 1.45. So why am I going to do that? So we can make sense of what this would calculate, okay? What would this integral calculate? Well, if we go from 0 to -1, sorry, -1 to 0, t equals -1 to t equals 0, right here. So remember, we got this formula from the exact same formula that we did for y and x, summing up vertical sticks from left to right. So what area will this first one find? From t equals -1 to 0, summing up the vertical sticks under the curve to the x-axis. Can you see it? All the way down to?
0.
To the x-axis, right? Okay. So what area will this first integral find? Can you see what it will be? It'll be just this, the curve from here to here, all the sticks down to x-axis. So I'll shade it. Ready? Okay? So that crosshatch is for this integral here. And now we're going to go from t equals 0 to 1.451, which is going to be this. And what area will that find?
The area under that curve.
The area under this curve. But we're going from a higher value of x to a lower value of x. So this will give that area, but it'll give the opposite of that area because we're integrating from right to left. Since we're integrating from the x right most x value to the leftmost x value, we're going to get this area for that second integral, but it will get subtracted. So this will be a positive area. Well, all areas are positive, but and this will be negative areas. Why? Because as t goes from 0 to 1.451, x goes from right to left. So then the resulting integral will be what? The resulting integral will represent what? Will it represent? The area. Can you see what area it'll represent? Yeah, like within the curve. It's like the area inside the curve here because you're going to have all this minus all of this. So it's going to be, what we're going to get is we're going to get this area right here. And that's the worst cross-hatching I've done all day. I'm trying to save it. Did I succeed? Not bad. Okay. A little more here. Oh, did you guys want to leave? Sorry. Okay. All right. So, so that red shaded region is what we get for the whole integral. For the whole integral. So, starting at that point, -3,6, and then if you integrate until t equals 1.451, you actually get the area inside the curve, and it works out following the logic of what these give you in terms of x. So, old way. Okay, so let's predict here. So this is let's find these. This is about 3. This is -2 and 1. So this is about 3 units. And this is 4 right here, from here to here. So if we were to predict that second integral, about how much?
12.
In the ballpark of about 12 square units, right? It's about 4 up there. It's about 3 wide, something around 12 square units. Okay, and so then, what's this? This is about 5 tall. Yikes, on the average, what? 1 or 2 or something? But anyway, so let's just put this one in. We'll just put this one in and see that it's 12. And then would you think that the red shaded would be bigger or smaller than 12? How about? Would we think that's bigger or smaller? A little smaller? A little smaller, okay. So we're guessing this is smaller than 12. Maybe 9 or 10 or 8 or something. And we're guessing this one's 12. So let's put those in and see what we get. I think I already did somewhere. Here. So we want from 0 to 1.451. Why doesn't it give me something? Is this my Q function? What's G? Oh no, I need to erase that. This is it right here. So from 0 to 1.451 is, there we go. Look at that. So 11.57. But notice that it's negative. So I just did this. I put in Q, which is our y function, right? Times the derivative of x with respect to t. So I'm following the formula here. From 0 to 1.45, let's do 1. And we get negative, what do we think it would be? Around 12. And negative, right? Because it's going backwards from right to left. Negative 11.57, we guessed it was 12. And then if I go all the way from, if I go all the way from -1 to 1.451, positive or negative, first of all? Positive and smaller than 12. $10.62. So now you could multiply this out, get a long polynomial, and do that. We're not going to do that. This is the technology here to show us that the numbers make sense. Okay, so going backwards, we got like a -12 here, and then we knew this would be positive area. We guessed less than 12, and we got it. So you're going to need, so for these area problems, you need to get a picture. All right, you're going to need to have a picture so you can interpret correctly what you're doing to solve these problems about area.